Okay. So now we can start. Welcome to this session today. So today we'll be discussing about topography and bathymetry of the model, how to design the grids and grid resolution, etc. Everything. So, sir, you may start now.
Okay, good morning all and welcome back to our ODTM workshop session. Today I will be taking the lecture, giving the lecture about topography generation of the model. So this is going to be a short lecture, doesn't have to be a very full-fledged, and also most of us work from home, so forgive if the audio video quality is not up to the mark. At any point of time, if the audio or video is not coming proper, then inform. So we will think about continuing it or not. So what today's discussion basically about how to generate a topography for running ODTM. So in the last few days in the workshop, you have seen what is ODTM. You have seen, you have learned how to get the ODTM code from the GitHub repository, and then you have also learned that how to port the code in Pratish or Aditya in our system, in our institute, and how to run the model. That lecture also was given by a couple of our colleagues. And so now everybody who attends this series of workshops will know how to run the model with the existing setup or pre-setup. Now, a little more information we need to provide that suppose you want to design your own experiment, say you want to run for particular ocean application, say Indian Ocean or Pacific Ocean or Indo-Pacific Ocean, then you need to set up the model. So setting up the model starts with the setting up the model domain. So model domain is important because that's the one the decider for what experiment is running. So I'm going to share my screen to start with. So if somebody please confirm my screen is visible.
Yes, it is visible.
Okay, so this is a topography generation on part of ODTM workshop. So we are going to give you information in this today's lecture. First of all, we introduce what is the topography file, okay, and what are the essential elements of topography file, and how to generate a topography file for ODTF, and how to modify a topography file. So these are the essential contents that I am going to discuss today. Okay. So as I said, topography is the basic first thing to do when one decides to set up the model for a particular application. They have to set up the domain, and this will contain the information about the resolution of the domain, the extent of the domain, boundary conditions of the domain, and the land ocean boundaries of the domain. All concepts will come in this particular file. Okay, so this is a particular module. It's called topography module. So to go ahead, I have to introduce the design of ODTM computational grids. So ODTM is casted in a C-grid configuration. So what is a C-grid configuration in a numerical computation is that it is a staggered grid. So if you see, there is a sketch of a few grids are shown here. Here there are three different colors are shown. For example, if I follow my mouse pointer, the red color grid represents the V grid. V grid means the V velocity or the meridional velocity grid of the model, and H is the thickness grid, the height or sea surface height or thickness grid, or the tracer grid of the model is with this H grid. And then we have a green color is called U grid. U grid is represented with a green color box, and then we have a black grid called a topographic grid. So let us identify how they are structured. So for example, let us start with the H grid. So H, let us focus on this top left part of this grids. Okay, so this portion has all the four colors overlapping with it. Say for example, H1 is at the center of this particular box, okay, and this particular box is actually, we can call it as the topography grid, okay. In the topography grid will however have corners. The values of each grid will have values at the corners, not at the other places, okay. Whenever there is an interjunction, they will have values. So in the topography black grid, the H1 is sitting at the center, okay. So in the center, H1 is sitting, and U1 is to the left of it. So U1 is the velocity, zonal velocity, which is coming at the left of the grid, and U2 is at the right. Okay, and V1 is at the bottom, and V2 at the top. So for a given H, there will be two U components on the right and left, and there will be two V components on the top and bottom. So this kind of staggering is called a C-grid configuration. So why we need to design a model in such staggered grid? Because it is for the computational stability. The first straightforward method is to stagger all the variable at the same location. But in such a case, when you construct the finite difference forms, you will have difficulty, computational difficulty. There are conditions in the numerical computational dynamics. So the condition has to be respected for a particular grid to be stable, giving stable solution. So that's why we kind of stagger the grid in this particular manner. Okay, so this is a typical C-grid configuration for Arakawa C-grid configuration. ODTM is casted in this C-grid configuration. Okay. So now the next important thing is what is a topography grid? So topography grid looks like something like this. Here a coastline geometry is brought, it's a cartoon of Indian subcontinent and Bay of Bengal and going to the southeast and then Australia is shown here. So in a topography file, what you will have is a land cell and an ocean cell. They are square cells, okay? They do not resolve along any particular coastline curve, but they represent only certain squared shells because that's how the model is designed. Okay, so the land cell is shown in magenta, and the ocean cell is shown in the white color. Okay, so you can see that the coastline is now resolved along this magenta border. So that is how we resolve the model grid in ODT or in any model, for example. So now that is why the resolution of the model is important. For example, the grid resolution and the coastline topography are interlinked. So if your model is of a very coarse resolution, then your grid boxes will be very large, right? Your individual grid boxes, grids will be grid segments will be large. So for a particular given coastline, you may not able to resolve it properly. You will only get a rough value or rough representation of the coast, which is a coarse resolution model. But if you have a fine resolution model for the same coastline, then you see that the coastline is more or less resolved better. So the more the finer the resolution, you have to resolve the coastline better and better. So that's why we see that if you want a realistic simulation of a model, we need to have a higher resolution. One reason is that with such a higher resolution, you will be able to resolve the coastline boundaries properly so that your ocean and land will be represented well in the model. So that is why resolution of the model is one of the reasons why the resolution of the model should be fine. Okay, in this case. Now, in the ODTM, there are these grids are this you can have a resolution which is a constant resolution, also a spatially varying resolution. So what is a resolution? Resolution is nothing but the thickness of x and y or dx and dy elements. Okay, so each segment of this grid representing a finite volume of the ocean. Okay, so it will have a delta x thickness and a delta y thickness. That's called model grid resolution. So if so now this cartoon shows that throughout the model domain, right? Throughout the model domain, you have a constant resolution. You have equal number of, equal width of the delta x for every cell. If you take any cell within this grid, you have equal width of delta x and equal width of delta y. So this is called a constant resolution model. Okay, it is not a spatially varying resolution. So ODTM can have a constant resolution. Also, it can have a varying resolution. So spatially varying resolution. So why is it important? Say for example, in a given experiment, suppose this bigger domain is your total model domain, and you want to focus on a particular area of the ocean with a higher resolution. Okay, because if you focus the entire model domain with a higher resolution, your number of grids will increase enormously. So which will have difficulty for computation, right? You will have a lot of computational time if required. How instead of that, you may focus or zoom in a particular area of the ocean. So in this cartoon again, I am showing the Bay of Bengal is a typical case, right? This is the Indian Peninsula, and then we have a Bay of Bengal and going to the southeast region. So in the Bay of Bengal, I want to have some process study with a higher resolution. So then I should design the ODTM grid. I will have a 3 zones in this design. For example, a zone 1, a zone 2, you will have a high resolution in the X direction, and a zone 3, you will have again the coarse resolution. Similarly, I need to increase the resolution in the Y direction also. Then only I get a net effect in a particular domain. Both X and Y are in high resolution. Okay. So for that, again, I will have a zone 1 in the Y direction, zone 2 in the middle, and zone 3. Oh, this is zone 3. Okay. Zone 3 in the remaining part. So if you design in this fashion, you will have a focused zoom the resolution in a particular part of the ocean. So, but one caveat of doing is that when you increase the resolution in X direction in a particular zone, even if this it will also increase the zonal resolution in the rest of the part of the model within this zone, even if this is not focus of your study. For example, you see in the zone 3, zone 2 segment of this domain, sorry, zone 2, zone 3, na? X is zone 2, Y is zone 3. I'm sorry, this is zone 3. Okay. So zone 2, zone 3 segment, you also have a larger X resolution, but weaker Y resolution. But still, this larger X resolution is not a requirement of the model, but we have to run it this way. We cannot escape, because we have this. We can increase the resolution only in the throughout the model. We cannot increase the resolution only in a particular XY segment. We have to increase in the entire X or entire Y. Okay, so that's the kind of a limitation. Similarly, in the east-west direction also, you have increased the resolution in zone 2 in this Y direction. You have to increase, and that will go all along the model, even if your research is nothing to do with the other part in this particular red color box. Okay, but doing so, like a cross mark, you get a focused area. The intercept of these two, you will get a focused area where you have a higher resolution. In most of the numerical general circulation models, this is the conventional method followed, because this has an advantage, because it can this high resolution can be incorporated or nested within the single model domain itself. You don't need to run different models at different resolutions and boundary condition sharing. No such problem happen here. There is no boundary condition sharing, and naturally the solution from the outside will propagate to the interior high resolution and will exit through the other side. So this is a more of a realistic way of doing it. But one problem is that you will be running the model with a higher resolution, even in areas where you are not very much interested. So that is the caveat, however. And many global atmospheric or ocean general circulation models, they do such a focused zoomed runs, for example. So ODTM also has this facility for a spatially varying resolution in this particular method. Okay, so now we can just look into what is a topography file actually mean. Okay, and what are inside the topography file, or what are the variables that you need to supply to generate a topography file. Okay, that is the major thing to consider in this workshop, in this lecture. So there are 3 bullet points I have written here. I will read it for you. So the first point is, this file the file containing the land ocean information as a mask, either 0 or 1, is called a topography file. Okay, topography file nothing but a mask file which contains 0 for land and 1 for the ocean. So typically this type of file. Okay, so here this is a white color, you can call it as a 0, and magenta color you can call it as a 1. So that is and not that one, and this one here. The white color you can call it as 1, and the magenta color you can call it as 0. So 0 is land and 1 is ocean. So such a 2-dimensional file is called a topography file. So our intention is to prepare or generate this file, and this file will naturally contain the thickness of the X cell and the thickness of the Y cell, or the delta X and delta Y will be inherited within this cell. Okay. So now, second point is that in ODTM, the topographic file are just two-dimensional files of just 2 dimensions, okay, load into that, and as there is no depth level resolved. If you remember the vertical structure of ODTM, they are layered model, okay. We are not resolving the bottom topography. The very essence of the reduced cavity model is that you are putting the last layer as a quiescent layer, so bottom topography will not be held in the model, and the barotropic components are filtered out just by that basic principle or basic assumption. Okay, so therefore we don't have any depth information in the model. We only have the land boundary, the coastal boundary. So therefore it will be a two-dimensional load versus lat sized file. So topography in ODTM, the topography files are just 2 dimensions, load into lat, as there is no depth levels resolved. Usually, the coastline geometry is taken as 100-meter isobath. What is isobath? Isobath means the contour of constant depth. Okay, a contour of constant oceanic depth is called an isobath. If you have a topography file, what is topography file? It basically represents the elevation or the depth of any particular grid location of Earth's surface from the mean sea level. Okay, the mean sea level is taken as 0. So any region higher than mean sea level, we count it as positive in meter unit. Okay, so 10 meter, 100 meter, 1 kilometer, 2 kilometer, 3 kilometers. So if you take a positive direction, then topography file you can see the mountains like Himalayas and all you will see. And then if you go depth, for example, minus 10, minus 20, minus 100, minus 30, you will start to see the ocean floor. Okay, so topography file basically represents the orography of the region, which is positive values are representing above sea level, negative values represents the below sea level. Such orography files are available for scientists from eTopo. eTopo is a file produced by US, I think it's from US. Either geological survey or I don't know the source, but eTopo is the commonly used orography file. So how they do the land survey they do echo sounding in the ocean. So they summarize all the thing, and they have, in fact, as for to our surprise, very high resolution topography files are available, because above the ocean surface or above sea level, they can use the satellite to study the orography of very accurately, very accurately, even to a resolution of 1 meter or 10 meter resolution accuracy. But below the ocean surface, they can do rigorous echo sounding. Right, echo sounding is a method used to measure the depth of the ocean at any particular location. So echo sounded data they utilize along with the satellite data of the land surface, and all they can combine. They have generated a very high resolution topography file is available for the scientific community. So usually the coastline geometry we take as a 100-meter isobar. So now we can take the line at which the ocean is 100-meter depth from the coast. So that line is what our benchmark line. Why 100-meter? Because by doing 100-meter, we are kind of going away from the continental slope. I think you all are aware of what is a coast, what is a continental shelf, and the slope. Okay, so we are going away from continental shelf. If you are taking 100-meter from the coast, go 100-meter. If you travel interior of the ocean, your depth slowly increases. By 100-meter depth, you will be going out of your shelf region. The shelf is a very shallow region, which we have no way to resolve in our model, because we do not have any depth information. So we better take only the continental slope and onward. So 100-meter isobar if you take for the depth of 100-meter, contour of 100-meter depth if you take from this topography file, you will get a proper topography structure of the ocean from that depth and onward. So that is what we are going to depend upon in this topography generation. Okay. So now, what are the essential elements in a topography file? So let us get familiarized with what are the essential elements inside a topography file. So currently, in the topographic file, we call the name gridspec.nc. Okay, so in ODTM, we have to provide this gridspec.nc, This file you find it in your input folder. So you are already familiar with the input folder so far because we were running the model in the last lecture. So in the input folder, you need to provide this gridspec.nc file. This contains all the information required to run the model all the information about topography to run the model is contained in this file. So what are the contents in this file? Here, the RKMT. This is actually the topography variable RKMT. It has a dimension of x size and y size, or total lawn into total land. Okay, so this is the relief of the surface of the earth. So RKMT. So this RKMT is what this particular file. Okay, this file is called RKMT. So this will run from I equal to 1 to the lawn and j equal to 1 to the total land. So each this will have an ij point for each of this segment, right? So that will have a value either 0 or 1, right? So this variable is called the RKMT. So RKMT, if you plot, you can see the topography of the model. So that's the essence of it. So if you open the file gridspec.nc, we'll open in a while. We are going to open it and see. If you open the gridspec.nc file, you will see the file for the variable called RKMT, and this is the topography file with the size, total lawn into total land. And there are other 4 variables given here. So what are they? This is a geo lawn underscore t. This is actually the coordinate of the longitudinal coordinate of the tracer cell is called geolon t and geolat t. So this is a longitudinal coordinate, latitudinal coordinate of tracer cell T cell. And this B, geolon B and geolat B, represents the boundary of a particular cell. So for example, assume this is a grid, this red color box as a cell, then you will have a boundary bottom and a top. So that boundary bottom and top is represented as B. And similarly for the lat also. Sorry, for the lawn it is left and right, right? So 2 boundaries are there for this particular grid. Similarly, in the lat also it will have a top and bottom boundary. So that is represented by B. So definitely that will have 1 number extra as compared to the total. So if it is 449, this geolat B will be 450 points. And if it is 298 lat points, then the geolat B will have a 299 lat points. So that is how this geolon B and geolat B are used. Actually, these grid centers are required to calculate the resolution of the model, right? So that means the geolon T I plus 1 minus I will give the x directional thickness of the tracer cell. Similarly, J plus 1 minus J will give the y directional thickness. So this is how the model calculates the resolution. What is the resolution? The thickness for the delta x and delta y of a particular cell is called the resolution of it. Okay, so this resolution information the model gets from this variable geolon T, geolat T, geolon boundary, geolat boundary. So these are the 5 variables in a topography file that ODTM requires. So I repeat. So the file name should be grid underscore spec.nc for grid specification. That's why grid spec.nc. You should find this file in input folder. So you should keep this file in the input folder. So where it will the model look for this grid specification. The file should contain essentially 5 variables, and this variable name you cannot change. You should give only RKMT because this is hardware in the code. Your FMS read input output based on this variable name RKMT. If you want to change, you should change in the code also. So better you give RKMT as the variable. So values of RKMT will be what? Either 1 or 0. 1 represents the ocean, 0 represents the land. Okay. And geolon T, geolat T, all are the respective latitude and longitudinal values, right? And the boundaries of the individual cells also. These are the essential elements of a topography file in ODTM. Now, how to generate a topography file or ODTM? So when you get the code from Bitbucket, you might have got the code along with that topography already in your input folder. So you need not generate in your experimental run. But when you do a real research, your first task is to generate the topography file, right? According to your research purpose. So now in this today's lecture, we will learn how to generate a topography file for ODTM. So topography files are generated in the topo folder in ODTM. This topo folder usually is inside the ODTM directory. So I'm not sure in the Bitbucket this topo folder is incorporated already. If it not, maybe Shikha may help you to incorporate this topo folder also there, so you can get pull in the next in today or next lecture. You can get pull and get a topography folder by yourself. So that will give you some idea how to generate it. So today I will explain and also try a demonstration how to generate. Maybe everybody can do that if you want to do it on hands-on today itself, or you can just see. It's very simple. It's not a very rigorously to be done. It's very simple to do. If you follow these steps, you will be able to generate the topography folder well. So topography files are generated in topo folder of ODTM. It usually inside the ODTM directory. ODTM is the directory where you find SRC, you find the bin, you find work, all those things you find in ODTM directory, where you will also have a topo folder. Inside that, you have all the things that you need. Now, the following utilities are required for generation of topography. So for topography generation, you need to have the following modules. So there are two ways of generation of topography exist in ODTM. One is by a combination of NCL software and Ferret software. Okay, NCL is a NetCDF, I mean it's an extensive data analysis and NetCDF handling software provided by INCAR, I think, but it may be discontinued, may have discontinued, but the code will still work. I don't think the code has any problem even in future also. In the far future, if this is discontinued, then we will have to regenerate the code in some other language. But anyway, the present language is NCL. We use to generate the code, generate the topography file, and then we use Ferret for further fine tuning. Okay, the fine tuning of topography we do through the topography. Sorry, for the Ferret software. Or we can equally do with a Fortran routine and Ferret. As a combination of these two software also we can achieve this. But this has been discontinued from the FMS version onward, because this was the exercise we done for our serial version, but now this is discontinued. This Fortran Ferret is not supported anymore. But we better use NCL Ferret module for generation of topography. Now, a topography NetCDL, we also need a topography NetCDL file or a orography file of ETOP of 5 or higher versions. This is also a prerequisite, because from there only we will generate the file. Okay, so the topography NetCDL file is required of ETOP or higher versions for generating our ODTM topography. So these are the essential slides I have prepared for you today. Now we will directly go to how we will generate the topography file. So let me open Aditya. So I will be doing this in Aditya. So you can also do this in Pratyush also, provided NCL is also available in Pratyush. So this is my Aditya folder, and I think everybody is seeing this screen. Is screen visible? Okay.
Yes, yes.
Okay, so now see, this is the my I was explaining in the ODTM. You will have a bin folder, execution folder, scripts folder, source code, work, etc. So here I have also a folder called topo. Maybe Shikha, we can incorporate this topo folder into our bin bucket. Maybe you can add it, and then they can either now or maybe end of today's workshop we can do, so that everybody will have it also. So now inside this topo, if you go, I have you have all required files. For the workshop per se, I have they copied everything for ODTM workshop folder. Okay, so now we will have only a clean folder called the ODTM workshop, in which actually basically whatever topography generation required is contained in this particular folder. Okay. So what are the essential components I have kept there? There is a ETOP of 5 NetCDF file. This is a grid spec. This is what the outcome. So I already run the code, that's why I have an output. And this is the main grid.ncl. This is the script used to generate the topography. And after generating topography, you may require some fine tuning, some modifying topography. Suppose you want to modify some fine shaping of some islands or something, you can do it in a separate folder, which is provided as a separate folder in this folder. Okay. So now let us get familiar with the. Let me open my Xming also. Yeah. So let us get familiarized with what is this eTopo. So this eTopo file is an XCDF file. It contains a rows. Rows means the relief of ocean surface. It's called the rows of the Earth system. So this has a resolution. This is a global data with 4,320 grids in X direction and 2,161 grids in the Y direction. So let us plot and see what is this rows. So the rows look like this. It must be a file which contain information in meters, which is the sea level, above sea level and below sea level, height in meters. So relief of Earth surface in meters. So this is the file called ROS. I am working from my home, so it will take some time to load. Yeah, so it is almost complete. So this is called the relief of the surface of the Earth in meters. So you see that there are both positive axes from 0 to 8,000 meter. That must be the height of our Himalayas. Himalaya is 8,400 meter, right? So that is Himalaya. You can see in the Tibetan and that area. You can see elevated landmass. And and you see near the coastline, you see about 0. 0 means the sea level. And the dark green, blue, and magenta line shows the negative value. That means it's below the sea level. So you can see it in the ocean floor very nicely, right? There are ocean floors are also having a lot of mountains. Right? It's not like a
Yeah, I think we lost the voice.
I'm sorry, I think I went offline. Is it visible now?
Not right now.
No, I mean, am I audible now?
Yes, yes, you're audible. Your
I'm very
voice got.
sorry today because from home, three people are connected. My kids are attending school, and I am also presenting at the same time. So tell me where I was actually, then I can.
So you
I'm
were
right.
talking about that the ocean floor is not just deep; it has mountains also.
Oh, very good. So I think now you see my screen, I guess.
It is still coming. Yeah, now I can see it now.
Very good. Okay. Thank you. Sorry for the interruption. And so you see that the topography file contains the essential elements such as, this image contains the elevation and the depth of the ocean surface from the sea level. The ocean floor also having some interesting mountainous region, right? Mid-Atlantic ridge, which is the raised floor mountain due to the spreading of the sea floor. Is a newly formed mountain, right? And because of the spreading of the sea floor, and Atlantic in the Pacific also you see some mountain, and in the Indian Ocean it goes all the way and cut the Indian Ocean into half this mountain actually. And so this is a kind of topography file called ROS. Okay, so now I'm exiting from this, and then I go to the script called make grid.ncl. So this is done in NCL script NCL language. So there are few places you need to give a user input in this code. So what are the user input? The user inputs are in the first few lines, maximum up to 15 lines. That's the user input. Just the code will be running on its own. So what are the user input it has to give? One is the first parameter is ng X. So actually this is telling you about the number of zones in the topography in zonal direction. What are those zones I described already? If you have if you decide if your model need a very special resolution, you can subdivide your domain into zone 1, zone 2, zone 3. So this number of zones, so this variable NZX represents the x directional number of zones. So you have 3 zones in x direction. Similarly, you are opting to have 3 zones in the y direction. So this represents the number of zones in the x and the y direction. In this particular example, there are 3 zones in x direction and 3 zones in the y direction. Next, shows the start and end longitudes for each zone. Longitude, the x represents the start longitude and the end longitude of the each zone. I mean zone boundary, the longitudes of the zone boundaries. Okay. So in my experiment, I want to say my origination should go from 30° east to 120° east. That is my total size of the domain. Within which I would like to have a 30 east to 80 east a typical resolution, and 80 east to 90 east, I need to have another resolution, and 90 east and 220 east, I need to have another resolution. This is my design, for example. In this particular example, you can choose any boundary, any zone structure in this way. Okay. So if you have three zones here, you should have 4 entries here, because then only the boundaries will be represented. Now, the next variable is dx, which is the resolution you want for within these zones. That means between 30° to 80°, I want 0.5° resolution. Okay, and 80 to 90, I want 0.25° resolution, and then 90 to 120, I want 0.5° resolution. So I am going to make a coarse resolution at zone 1 and zone 3, and a high resolution in zone 2, in the middle zone. So that is the x directional information. Now we have y direction. So y, we have my model domain goes from minus 30° south to plus 30° north. So this is a tropical inclination configuration, and within which I have also 3 zones, right? So what are my zones? Minus 30 to minus 15 is y1, my first zone, and then minus 15 south to, or 15 south to 8° north, my second zone, and 8° north to 30° north, my third zone. Okay. Then within this zone, I would like to have this many resolution. The first zone, y direction, I need a 0.5° resolution, and in the middle zone, I need y directional resolution 0.25, and then okay, and then
Hello.
Yes, yes.
So I think again disconnected, na? You know.
Yeah. Uh,
I'm sorry, I got again disconnected.
yes.
I think it's not going to be very smooth today. Okay, so I continue. So the screen shows that my y directional resolutions in 3 zones. Okay, zone 1, zone 2, and zone 3. Then the next variable we need to know is the NXSM. Okay, what is NXSM? NXSM represents between the zone there should be a blending in distance. For example, if I mark here, if you follow my screen here, are you seeing the PPT now? Can somebody confirm?
Yes, yes, yes.
Okay, I'm sorry for the frequent interruption. So if you see the zonal boundaries between zone from zone 1 to zone 2, there is a transition, right? So you cannot just give an abrupt change of resolution. It will create a lot of shocks called numerical shocks in those abrupt change of resolution. Rather, you slowly blend in, okay? From zone 1 to zone 2, within a region of a few degree thickness, you slowly blend in the resolution. So there will be a smooth transition from zone 1 to zone 2 and zone 2 to zone 3. So this is the transitional boundary. So that how much thickness you need for that blending in. If you give a very large thickness, it will start to blend from a very long distance away from the boundary and then blend in. And then if you give a very short distance, it will really quickly it will blend in. So it is up to the researcher how to choose that zonal thickness you want to blend in zone. Okay, you can call it as a blending zone. in the x direction. Similarly, you have a blending zone in the y direction. So that is what we describe by NXSM and NYSM. Here I give a blending zone of 5 degree thickness. Then in all the direction, let 5 degree be the thickness. That model will decide. This script will decide from it take 2.5 degree to the left and 2.5 degree to the right. It slowly started blending these two zones in the zonal boundaries. Okay, so that is the blending zone thickness. I'm giving you the 5 degree. This is the unit is in degree of the blending zone. So only these are the input you need to provide to this routine. Then you will get the topography. And to run the script, you have to just come out and then you can run the script using NCL. So NCL is the command to run. Okay, NCL make grid dot NCL script. Okay, if you run this script, it will take some time, not very long. Okay, so it has completed. So the whatever written here, you don't need to pay much attention. It is giving some dimension and it's how the code works and etc. is given. So at the end of running, you will get this file gridspec.nc. This is the file you are going to get after simulating, after running this code. So gridspec.nc. Then what is inside this gridspec.nc? So you can open it and see. So this my gridspec.nc, as per my resolution I have given, it has generated a geodon underscore tracers grid, that underscore tracer grid, boundary grid in yon and lat, and then RKM with the size of 199 points in x direction and 165 points in the y direction. So now let us plot this. For example, RKMD. If you plot, we will see how the plot looks like. Hope it will load quickly. Yeah, so this is the, everybody see the plot? So can somebody please confirm?
Yes.
Very good. Okay, so this is the plot. This is the topography file it generated. So what you see here, you see Indian Ocean, right? You see Indian Ocean, and you see the land ocean boundary of the Indian Ocean, which may be not familiar picture for you because we have taken the 100-meter depth as the reference line. So this is how the 100-meter depth contour of the land ocean and boundary looks like this way. So what are you seeing here is that value 0 represents the land, 1 represents the ocean. Okay, there are only two values here in this file. So this is from 30 degree east to 120 degree east and 30 degree south to 30 degree north. So this is the typical tropical Indian Ocean domain. Now you also see a lot of dots surrounding, dots within the ocean. So they are actually the islands because we've gone 100-meter deep. Okay, even some small, some very high mountains now exposed into the ocean. But these islands exist. For example, this is the Lakshadweep Islands. You will be seeing the left side of the Indian Peninsula, right? The Indo-Arabian Sea, Lakshadweep Islands. And then there are islands in the Andaman Islands. You can see in the Bay of Bengal where my mouse is moving. That is actually Andaman Islands because our resolution of the model is 0.5 degree we have given. So it will not be resolving very well. I told you in the presentation earlier, if you remember, to resolve the model very well, you need a very high resolution. If you give false resolution, 0.5 degree and all are not very good resolution for small islands. You may need to give a 0.1 degree and all to get the islands better. Okay, so that limitation will be there. So here we see that there are Andaman Islands is resolved just as a square box. That much only it can resolve. And this one small dot in this near the Gulf of Aden is called the Socotra Island. Okay, Socotra Island is only one dot. And this must be in the Maldives Islands must be somewhere here. And this is the Masquerade Islands and Christmas Islands and many other dot and spots are visible. So this is how the raw topography generated file looks like. Okay, but this may not be a good choice to go ahead with an experiment because such small dots for one grid cell size and all will generate unnecessary numerical noises in the solution. So better we smooth it. And another thing is that there are some potholes you can see. For example, see between Java, Sumatra and Indonesian landmass, there is a pothole. What is a pothole? Very close to isolated water body. It has no consequence to our model. So better we fill these potholes and make it tidy. Okay, so we need to tidy up the topography. So that is the next step in the topography. We call it modified topo operations. Okay, so I think by now you all understood how to generate a topography. I will explain again. So we have to use the script inside the topo folder. The script name is makegrid.mcl, which has few user input. It's very simple. It is written what are the inputs is required. And after giving the input, you run the code in MCL software. Then you get this gridspec.mc topography file. Okay. Now let us modify this topography. So to modify this topography, to tidy it up, you can go in modify topo directory, which is also provided along with the code. And this folder contains certain modification scripts. This runs in Ferret. So here you need a Ferret to modify the topography. Okay, so there are certain certain hardware codes. You don't need to worry about what are those codes. You only need to worry about two important programs called fill land.jnl and fill ocean.jnl. These two scripts will fill your land as per your requirement and fill the ocean wherever you require. So these two scripts you can alternatively keep use. Okay, as many times as you use, you can keep on modify your topography. We will demonstrate how this is happening. So let me clear this. So this is clear screen. So this is we are now inside the modified topo directory, which is one step away from our topo folder, right? So two important files are this fill land and the fill ocean files. Okay. So now what we have to do is we have to copy the just generated grid spec file to this folder. We have just generated in the previous folder, right? We just copy it here. Okay. So we can verify we have copied our grid spec here. So this will be this is just the what we have seen. The shade RKMT will show the same file. I think it has come. Yeah, so this is the file we have just generated. So you copy it in this folder. Okay. After copying it, so I'm going to fill some portholes here. So I should use the script Ferret. I open Ferret. Go fill land. Okay. So if I run this script, what I will get is a window. Just wait. It may take some time to load. Okay. So this is my my land fill script. So now this has opened the topography you have generated and showing in front of you and asking the script is waiting for you to modify this. Okay, so you can modify now the script is for filling the land. So you can do some land filling. Where are the places eligible for land filling? For example, these potholes we can fill. And this particular area in the South China Sea, we are not interested in the sea because it is coming out of our Indonesian domain. We can fill this with the land. That many computation at least will reduce. It will help us, right? So we can fill the pothole. Another pothole you see near the Mumbai, Gujarat, this continental slope. You see some pothole. You can fill that. This for example from Gulf of Aden to this this the Suez Canal. This sea, so here we don't need this pothole. It's like an isolated way. We don't need any. We don't have any consequence with this. We can fill this also. And so there are several things to fill. So how to fill is very important. Please listen carefully. So this is a cursor is moving around. So this script is made in such a way that you can click as many area as you want. So I am clicking. So then you must be seeing some cross mark appearing on the screen, right? So you just keep on click. Okay. Wherever you want to fill the land as a closed loop. So I am clicking all the way here and so I made a circle of clicks. Okay, so it looks like a circle of dot which I made of clicks here in this monitor. After you complete your click, you go to the leftmost part of the grid. Outside the figure, you click again there. That is the signal for I have selected my domain. I completed my selection of my domain. Now it is calculating a modified topography. See, now those portions now got filled with the land. So this is the fill land routine. So now you can do this exercise as many times as you need. So once you're done, then you have to close, exit. Again, we can repeat this with the fill land. You can fill more land. There are more potholes to fill. So you can repeat this as many times as you want. Each time you have to exit and end. Okay. Then only this script will work. Now, there is a filling. I want to fill this ocean, this basin. This bay is basin is not much of our interest. So I'm going to fill all the way from here. You can click clockwise or anti-clockwise, any direction, no issue. Okay, so you have completed the selection, and then you tell the script, you click outside the plot area, then click, that is the symbol for that you have made your selection. Now the script will fill land in that particular area. Okay, so that area also got filled. Now what are the areas to tidy up? There must be some area near the Mumbai area, right? There is some pothole. We'll fill that up, and the rest we will leave, and then we'll see how it looks at the end. Okay, so now again I'm going to fill. Okay, so in any case, don't click inside the domain, inside the plot area by mistake. Then you have to open the file. Okay, again, otherwise the script will not work. So actually, now the script is waiting for your input by clicking. So now I'm going to fill this particular area. I can very carefully go ahead with this. It requires some patience. Don't click wrongly, then it will generate an artificial land. Okay, so I have filled that area also. Okay, so now I have filled almost the porthole. Also, you must be noticing that there is a additional some boundary, filling also has happened in this script. This is also kept active because our model is a closed. I mean, the boundaries are closed boundaries, not an open boundary condition in ODTM. So that's why your all boundary should be a land boundary. So I have closed this, and this also script automatically closes to grid from the original boundary as a closed boundary conditions. Okay, so now our model domain, all the lands are tidy up, and then now we have to take care of some of the islands. Either we have to represent these islands with a bigger size. The single grid and island and road will not work because it is a C grid configuration, right? So you need to have a U, V, and H all should have a mask of its own that it will generate within it from this RKMT file. So better to either you increase the size of the island if you want an island, or you remove unwanted small chota island, you remove, because the scale interaction of the dynamics with the island, then the island should have a certain size of the scale of the problem. What is the scale of the problem? Basically, we are looking at baroclinic dynamics of a size of several hundreds of kilometers. We are not interested in the solutions of very few meters of waves. Okay, so beach waves and all are not our concern. Our solutions are large waves, which can, so topography impact such large wave if the topography itself has a size of that wave, or the in almost similar order of that size of that wave. So an island of, say, for example, and a size of an eddy, for example, will have an impact. But a dot like this may not have any impact in our solution. So better we remove it rather than creating unnecessary noises. So to remove the islands, now I will use the next script, which is our fill ocean. Okay, so I'm clearing the window. So I have one more script called fill ocean. So I'm going to use that fill ocean. So fill ocean. So I can now fill some ocean. Fill means fill the topography with the ocean body. That's what fill ocean script. So if the operation is same, the file which you have just now generated again loaded in front of you and asking you to fill the ocean as you like. So I am going to remove all these Lakshadweep and Chota islands from here. So so I can click surrounding that island and ask the script to fill ocean instead. Regular selection. Then I completed my click, and then go out the plot area. I am clicking here. So it is giving an information. My selection is over. Now it's going to fill the ocean inside. Okay, so now that many islands got disappeared. They all replaced with the ocean body. Now there are some more to take care. For example, in this Andaman area and these small islands, I'm going to remove. Okay, in the next step, I'm going to remove this island from Andaman area. I'm going to remove. So you can shape it as much as you like. So that many area I removed. That many small island chains I removed. Okay, that got shaped as well. Now that part is polished very nicely. Now there are few islands I want to keep. For example, this Mascarene islands. Maybe I would like to keep because they are so big in size. It's not better not to remove it. So, but I may remove other small islands surrounding that. I am going to remove to tidy up a little more. Okay, so now we can remove some unwanted islands from here. So along with this, there are some couple of dots also along the coast looks untidy. So along with that, we can remove all these small. So whatever is inside the area where you generated by clicking a closed loop, those many area will be filled with either ocean or land. Okay, so this is the shape I selected. Okay, so almost our domain is cleaned up. Now two islands I have kept two islands. If you want to thicken the island, you can use the script to fill land. Okay, then you can thicken the island if you want. You can make it more thicker, but be careful because those are artificial thickening. So you should not create so much artifact in the model. Now the same script you can use to create new channels. For example, the Sri Lanka and India are now connected. Suppose you want to open up this channel, you can use the same fill ocean script and click within this area very carefully. Okay, then you can open this channel. And now another thing is that suppose you want to do an experiment with some artificial bridges or channels, so you can use the same script. I will demonstrate one example for you. So I go back again and fill land. This fill land and fill ocean you can keep on alternatively use. Okay. Each time the modifier I want to use for further modification. Okay, so now let me say I want to study the impact of Andaman Sea in my experiment. This is Andaman Sea, right? So I want to study what? I want to study the impact of Andaman Sea in Bay of Bengal circulation. So what I can do is I can now generate an artificial bridge right away. I can create an artificial bridge separating the Andaman from Bay of Bengal. Then I can run this model with a control experiment with no Andaman with the Andaman Sea and an experimental run without Andaman Sea. Then take the contrast. So such type of topography modification we can do in this with this particular model. Okay. So I think this is the whole description of all the topography file. After doing all this exercise, what we will get is a file called gridspec.nc. So this will contain the essential element. But the process is not yet over because due to the modification of this the topography, you have lost other essential variable. This only has RKMP, right? But this file should also have other variable, right? For example, geo.t, geolat.t. So to incorporate this, one last step you need to do is that you have to run this script called the change header. After completing your topography modification, you have to run this script change header. So to run, it's very simple, /change header. So if you run this script, it will fetch the header from the original topography file and prepare it for the final file for you called gridspec.nc. And this gridspec.nc will have all the essential components, geolon lat t, geolat D, geolon B, geolat B, and RKND. And this RKND is what your modified RKND for your X. So I will show that plot also. So this is your module, and that's a very tidy. Sorry, here the Andaman I filled. You can remove that by one more time the fill portion script, and you can remove this land bit which you generated. Okay, so then you will get a very clean, modified, smoother topography for your and this script you can keep use for other generating artificial grids or artificial islands. You can if you are want to find out what happens, there is a very big island sitting in the equatorial region of the ocean. How the flow will get diverted. Just experiment. They are artificial case, but just for experiment or curiosity, you can do. You can generate as much topography as you want, and then do interesting modification to the model setup. So this is the end of today's my discussion. I think I have explained these things clearly that I was telling in the beginning. What is a topography file? We have already seen this. What is a topography file? And what are the essential elements of a topography file? That also I told you. Inside the topography file, you have a mask file and a latitude and longitude information of the file and the resolutions, etc. And how to generate a topography file. So we use an NCL script to generate a topography file with our user inputs, and how to modify a topography file. We use a ferret module to modify our topography. So this is a very simple module, and we can be easily learned. Today I did not give any hands-on, but it is very simple. Once you get the topo module in the bit bucket, you can pull it and do this exercise. And this gridspec.nc file, you have to keep it in your this gridspec.nc file. You have to keep it in your input folder, from where the model is going to take all this information. Okay, you have to keep this modified topography in your input folder. Now your model resolution, domain, everything will be defined from this gridspec.nc. The model will look at this file and then it interpolate the forcing files and do the simulation accordingly. So I think this is the end of the module of topography generation. So maybe I can now come out of the share screen.
I have a question.
Yeah.
Sir, what happens if we change the resolution in size, param.h or size.h? There is a file where we can define dx and dy.
No, those are obsolete now. They are not effective.
So if we want to change the resolution, we have to make changes in this gridspec.nc.
Yes, those lines are obsolete. Maybe some of us should note down in the code. They were discontinued. Once it became FMS, it is happening through here in the gridspec.nc. Yeah.
Okay. Okay, yeah. That is why Anju was changing the resolution, but it was not working.
Nothing happens. Not working. Have everything taken from here. The serial code we handle. Serial code also this RKMT file, but some control was given there also, especially generating snapshot output. But now after FMS, they have moved everything. Now they made a gridspec.nc is the base file. Only one file, everything there.
The next question is that can I make ODTM into a, I mean, just by changing grid spec into a global resolution? I mean, I make it for the global data. Can the model be easily turned into a global model?
It can technically, yes, but problem will happen when you go to polar region. There are polar singularities there, which is not dealt so far in the code. Especially in northern hemisphere, you will end up in converging domains, and then your latitude will shrink. Sorry, longitude will shrink to single point. So their model will not work at all. And it technically it can do. It can cast in that, but the model definitely won't work. And another thing is that the mixer layer module is maximum 250 meter grid only be provided depth. Yes. So, but with latitude, the mixer layer goes up to 500, 800 meters. So there it will not work at all. So this is basically, so far it's a good for a tropical ocean, Indo-Pacific, Atlantic, tropical from 40 degrees south to 40 degrees north, or 30 south to 30 north. This will work within easily. But other adaptation to higher latitude, we need to make more modification, especially the polar singularity issues and mixer layer. Actually, you can do mixer layer if you, instead of 250, if you give 800 meter, it can take, no problem.
Okay.
You have to increase the sabotage. So those need to be hardwired, I think. Hardwired, so we need to change in those areas.
Okay. Okay. Yeah.
Sir, I have one question.
Yes.
Why are we not using SRTM 30-meter resolution topography file instead of eTopo file? It has a better resolution, right?
Yes, we can use a different topography file also. There is no issue. We can use. No issue. So far I used demonstrated using eTopo, but other high resolution files we can use.
Okay.
Any more questions? Okay.
So maybe one of this topo module, maybe we can pull it to then push it to the Bitbucket. So that we will, maybe we can do when we come back to office, for example, and
Yes,
make sure everything is tidy, and then we can push so others can also. So far that module is not provided with the code, I think.
Yeah, I think so. It is not provided. I will have to check the source files once again, but I think it is.
Yeah, and the code that day we pulled, it did not have a topo. It only have other folders, the source code and things like that.
Yeah, so I will copy it from your folder and then later push it, and I'll email everybody, then they can pull it in their own directories.
Yeah, maybe we can do when the office opens, we can check files, only essential files are going there. Some
Yes.
garbage file. I mean, whatever module I discussed today only has essential files, so that much it can go. No problem.
Yeah. So yeah,
Rest
we can make a
folder
clean
can go.
directory and then push it.
Yeah, that's right. And provide that eTopo 5 also, as it's not very heavy, so we can generate
Okay.
out of it.
Okay. Then probably shall we close today, or if anybody has any questions, they can ask.
And how this video will come, okay, because it broken in between, right?
Yes, sir, it is. I mean, for the time being, it is okay. We don't have anybody to edit the videos. So, yeah, maybe later if we have somebody, we can ask them to just cut a bit of
Yeah, today
portions.
I think it's 3-4 pieces already. Yeah, the videos
Yes.
cut into 2-3 pieces already. In the
So I'll stop the recording now, and
yeah.
yeah.